Hi, and welcome to our online discussion this week. So this week we will be talking about limits. So before we start, I think it's best that we review the definitions. So if f is a function from Rn to R, and if A is a vector in Rn and L is some number in R, we say that the limit of x approaching to A of f of x is equal to L if and only if for all epsilon larger than 0, there exists a delta that's positive such that whenever the distance between x and A is smaller than delta, the distance between fx and L must be smaller than epsilon. So so this symbol means for all, and this symbol means there exists. These are just shorthand notions of these words. So another definition concerning sequences is that if xn is a sequence of vectors in Rd, where Rd is d-dimensional space, and if A is a vector in Rd, then we say that the limit of xn as n goes to infinity is equal to A, or we just write xn goes to A, if and only if for all epsilon larger than 0, there exists some natural number big N such that as long as small n surpasses big N, the distance between xn and A is less than epsilon. So since we're going to be dealing with limits, I feel like it's a good idea to introduce this following proposition that will make your life easier when checking if the limit of some multivariable function exists. So here's the statement. So suppose that f is a function from Rn to R, and A is a vector in Rn. Then the limit of x approaching A of f of x equals to L exists if and only if for all sequence xn in Rn, let's not use n here, let's use Rd, such that xn converges to A in Rd, we have that the limit of n goes to infinity of f of xn equals to L. So basically, this reduces checking this limit if it exists. So this proposition reduces checking the existence of this limit to checking this statement for just arbitrary sequence in Rd. And we'll see today using many examples that this will be very useful in doing some problems. So I think it's a good time now to pause and test your understanding to see why this proposition will be true. Well, as you know, in 2D, you're not required to know the reason why this works, but I really encourage you because if you really understand limits, which you should be able to see why this proposition is true. So here's the reason why. Again, this will not be on their test, but I feel this is just something that you should understand. So why is this true? Indeed, so I want to see that if the limit of x going to A of f of x equals to L, then for any sequence xn going to A, I have the limit of fxn equals to L. So let's first show that if limit of x goes to a of fx is L, then for all xn going to a, the limit of fxn is also equal to L. Indeed, by definition, of the limit, we have for all epsilon larger than 0, there exists a delta larger than 0 such that if x and a are closer than delta, then we must have fx is close to L within epsilon. But we also know that xn is a sequence that converges to A. What does this mean? This means, again by definition, there exists a large n that is a natural number, such that if small n passes large n, we must have that the distance between fxn and L, the distance between xn and A is smaller than delta, right? This is just by definition of a sequence converging to A. So then what this means is that if my small n is larger than big N, I have xn is close to A within delta. But then this condition in turn implies that f of x is close to L within epsilon. So it means I can find a large n such that if small n is larger than large n, my fxn is close to L within epsilon, which is exactly what we want, right? So this is exactly this definition. So the limit of n goes to infinity of fxn is equal to L. Great. So we have this direction done. So now for the other direction, we want to show that if for all sequence xn going to A, we have the limit of n going to infinity of fxn goes to L, or equals to L. Then the limit of x goes to A of fx is actually equal to L. Good. So let's suppose that this is not the case. i.e., that the limit of x goes to A of f of x is not equal to L. So what does this mean by definition? So by definition of limit, this means that there exists an epsilon larger than 0 such that for all delta larger than 0, there exists an x depending on delta such that we have x is close to a, x delta is close to a within delta, but the distance between fx and L is strictly larger than epsilon. Right, so we're just negating the definition of the limit. So what does this mean? So this means that there exists an epsilon larger than 0 such that for all natural number n, there exists an xn such that although the distance between xn and a is smaller than 1 over n, we still have, nonetheless, that the distance between fxn and L is bounded away from 0. And so, in this case, we've created a sequence xn such that xn converges to a, right? Because this is true. So xn converges to a, but fxn does not converge to L, right? Because this is also true. So we found a sequence that converges to a, but the function value does not converge to L. So this contradicts our assumption. Why? Because we assumed So we assumed that for all sequence xn converging to a, we must have the limit of fxn equal to L. And here we have a xn converging to a, but the limit of fxn is not L. So this contradicts our assumption. So this must mean our assumption is wrong. So what is our initial assumption? Our initial assumption is that the limit of fxn is not L, right? So it must mean that this assumption is wrong. So it must mean that the limit of x going to a of fx is L. And so we are done.